Welcome to the central force problem. Today we are going to discuss the Virial theorem. Uh, the Virial theorem concerns a statistical result which is different in nature from the previous considerations, as it is concerned with the time average of mechanical quantities. We begin with the statement of Newton's second law for a given particle I, and then we define the scalar quantity g as a sum over all particles I of a given physical system of a dot product between their momenta and their position vectors. And then the time derivative of g will be a sum of two terms. The first one is simply twice the kinetic energy, while the second one, by virtue of Newton's second law, turns into a sum of the dot products written here. So with this expression for the time derivative of g, we can then define its average over a given time interval or period tau, which is the integral from the initial moment to the moment tau of the time derivative of g divided by tau. And shorthand notation for the integration and the division by tau is given by the overhead bar over the quantity. And applying our previous result for the time derivative of g, we can write this average as a sum of the following two terms, the average of twice the kinetic energy plus the average of the sum of these dot products. And then if we perform the integral on the left-hand side, which is trivial, it follows that this sum is equal with 1 over tau multiplying the difference between the value of g at the time tau and the initial value of g. This right-hand side is going to be 0 if the motion is periodic and tau is the period, or if the motion is bounded, such that there is an upper limit to the values for the coordinates and velocities for all particles. In that situation, for a sufficiently long tau, the right-hand side can be made as small as desired. Then, if this quantity is vanishing, it follows that the time average of the kinetic energy is minus 1 over 2 times the average of the quantity written here. And this is the Virial theorem, and the right-hand side is known as the Virial of Clausius. Very similarly, we can treat the case of a velocity-dependent dissipation being included in the dynamics of the system. So in this case, Newton's second law would include, alongside with the applied forces, the frictious forces, but the procedure is largely the same. So we once again define the scalar function g according to the same prescription. We take its derivative with respect to time, and we evaluate each of the terms. In this case, the terms including the time derivatives of the momenta uh, will also have this contribution, which follows from Newton's second law, and as such, the total time derivative of g can be written as here. And if we now take the average of this quantity over some time interval tau, then we already know that the left-hand side is given by the expression here, and for the right-hand side we will have the sum of the corresponding free averages. We are interested specifically in evaluating the last term in the sum, where if we apply the definition of the average, we have the expression here, and it's very easy to work out with the method that we have employed in previous chapters to find the expression here. So now it is very clear that if we regroup the terms, we have a left-hand side that is quite similar to what we had obtained previously, but having the contribution of these additional terms and being equal with the right-hand side given here. So once again, provided that the motion is bounded, and in this case also sustained, so that it reaches a steady state, the left-hand side can be made as small as desired for sufficiently large time intervals tau. As such, the Virial theorem is recovered for the applied forces, and so this can be made to vanish, and as such, the average value of the kinetic energy follows as given here. It is important to stress that the motion must be sustained by energy that is pumped into the system, as otherwise all averages would reduce to zero if the energy would be fully allowed to dissipate. In the case of conservative forces, the Virial theorem implies the result here, which follows simply by writing the force as the minus the gradient of a scalar potential. And in the particular case of a particle moving in a central potential, then the expression reduces further to the one given here. Furthermore, if the potential is a power law function of radius, then the result here follows immediately. And this also will clearly hold if the potential happens to be a homogeneous function in the radius of degree n plus 1 due to Euler's theorem, which we have employed in the previous chapter as well, which would immediately furnish this equality in the given conditions. Also, in the case of gravitational forces, the index n over here is equal to -2, and as such, the conclusion of the Virial theorem is that the average value of the kinetic energy over a given time interval is -1 over 2 times the average value of the potential energy. As an application to a situation that is slightly different from what is habitually found in classical mechanics, we can look at examples pertaining to thermodynamics and statistical mechanics. Namely, we can consider a gas of n atoms occupying a volume V at temperature T. And we will use the fact that by the equipartition theorem, the average value of the kinetic energy for such a system is equal with 3 over 2 times the number of atoms times the Boltzmann's constant and times the temperature T. Now, if the density is low enough such that atomic collisions can be neglected, then an element of force exerted on the gas by the container constraining it is going to be equal with the product between the total pressure and the element, an element of surface, and the force is directed opposite to the normal orientation of the surface. That is, it's directed inward as it's keeping the gas inside. And as such, with this expression, it's really simple to calculate the sum here by converting it to an integral. So this is just going to be equal with minus p over 2 times the integral over the closed surface of the container of the dot product between the radius vector and the normal to the surface. And then by Gauss's theorem, this can be converted to a volume integral of the divergence of the integrand, and the divergence of the radius vector in 3 dimensions is just the scalar 3, so the entire integral is equal to 3 times the volume. And as such, taking this result in the Virial theorem, we obtain the well-known Boyle's law, or the law of ideal gases, namely that the product between pressure and volume is equal with the number of atoms times Boltzmann's constant and times the temperature. Now, let us assume that between each pair of atoms in the gas there is an interaction potential of the form given here, with m being greater than 0. And we will also assume that the gas density relative to each atom follows a Boltzmann distribution, given by the expression here. So in the vicinity of each atom, in the immediate vicinity, the density is essentially zero, so there are no other atoms around, but the further we go outward radially, we recover more and more of the gas. So now if we write the Virial theorem down, having both the forces of constraint furnished by the container holding the gas and the applied forces, we will find the expression here. So if this term was vanishing, we'd simply have the ideal gas law. Now, in order to evaluate the quantity here, first of all, notice that the single sum over all of the atoms in the gas can be written as a double sum where the applied force is explicitly assumed to be acting between pairs of atoms. And furthermore, given that this potential is central, we know that this force does not depend on the orientation of each pair, but simply on the distance between the atoms. So from here, we immediately get to here. And now we can break up this sum into two equal parts, which we can write as the terms here and here. And using the law of action and reaction in its strong form, we know that these uh, uh, these uh, these two terms will be equal up to the sign. So we can factor them together and to obtain the expression here. So now we return with this in the formula for the Virial theorem, and then we simply calculate f explicitly based on the expression of the potential to calculate the dot product in order to arrive at the result here. And now in order to evaluate this, we once again convert the two sums to integrals. So notice that the sum over I is going to give the same result every time, as it doesn't matter which atom we pick. The system is completely homogeneous from this regard. So the sum over I simply factors the total number of atoms. And then the sum over J, we just convert it to an integral over the volume of the gas, having the integral multiplied with the Boltzmann distribution. And then we assume that this volume is a sphere of infinite radius. So performing the integration over angles is trivial. It just results in a 4 pi, which multiplies n, and then we are left with the integral here. And in order to evaluate this, we perform the following change of variables. So the quantity here is equal to x. And then if you carry the calculation out, which is quite straightforward, you end up with the result here. So there's this constant, and then the integral here is by definition the gamma function of argument 1 minus 3 over m. And as such, the final result is the one given here in the box, and it represents the correction to Boyle's law when interaction between pairs of atoms are present of the type here. And notice further that in order for this expression to make sense, m actually has to be greater or equal to 4. So which implies that the forces must vary at least as 1 over r to the 5th power for this result to hold. Now, in conclusion, we have deduced the Virial theorem for the general case with and without velocity-dependent dissipation, as well as in the particular case of conservative forces. The result was applied in the deduction of Boyle's law for an ideal atomic gas, as well as in obtaining the correction due to central interactions between atoms. And in the following, we are going to discuss the differential equation for the orbit and integrable power law potentials. That being said, thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.